This is a brief lesson in history about fear and ignorance of extreme weather 500 years ago. Now, as impossible as it is to comprehend events in the 20th century without understanding totalitarianism, it is likewise impossible to understand Europe's 16th century without recognizing the role of superstition. Magic, witchcraft, sorcery, and superstition pervaded every scale of culture, from the smallest corner to the cosmic. Now, an equable climate had pertained in Europe about 1,000 years ago, and by the 14th century, that had deteriorated into a long period called the Little Ice Age. The Little Ice Age saw harsh winters, severe storms, and also extreme variability. That means you could see mild winters and then very severe winters, summer heat waves, droughts, sea storms, and floods. The Little Ice Age persisted about 500 years, abating only in the 19th century in some places. Now, the most severe period of that 500-year period of the Little Ice Age occurred in Europe between 1550 and 1700. That was also probably the harshest period of weather in the last 1,000 years, if not longer. Now, the severe conditions and climate brought about crop failure, starvation, disease, death, and social unrest. But it was already occurring in a period of great upheaval as the Reformation, the Counter-Reformation, and warfare battered Europe. Now, how unusual was this very intense period of the Little Ice Age? On the afternoon of August 3rd, 1562, a thunderstorm struck Central Europe across a front several hundred kilometers long. After raging for several hours, the storm unleashed a terrific hail that continued until midnight. It destroyed crops, it destroyed vineyards, birds, and unprotected horses and cows. Diarists then noted something that we hear today. They said for 100 years, such a storm had not been seen. The storm was deemed so unusual in this period of superstition that it had to be unnatural, it had to be supernatural. Thus, superstition and witchcraft bred a precautionary response. Eradicate those responsible for the storm and this period of new storminess. Now, it was well known that people could cook weather with the help of Satan. So, thus did extreme conditions of the severest part of the Little Ice Age contribute to Europe's most horrific period of mass executions and witch trials. This was completely legal, and it was administered by highly educated upper social strata. These are institutionally legalized executions for sorcery. There are many reasons for these trials, but some of them are related to weather cooking, that is, working with Satan to produce these fierce storms. The average, the estimates now are about 50,000 executions across Europe, and no country was spared of this. Now, there were skeptics who stood up, but they were often accused of, or threatened to be accused of sorcery to squash any debate. So legal philosopher Jean Bodin in 1580 noted that witchcraft was the most terrible problem facing humankind. Again, a very modern note. Bodin championed the international attack against skeptics like Johann Weyer. Now, Johann Weyer is a physician, and Weyer argued that the accused sorcerers seemed to be suffering from what he thought were medical conditions we would modernly term mood disorders. He also thought it was theologically impossible for Satan to work through such people to do his work. Weyer then declared that confessions that had to be extracted by torture, because there was very little direct proof of witchcraft, well, these confessions were extracted by torture, and he found this torture immoral. So the response was Jean Bodin decided to accuse him of witchcraft, and so any feeble notes of humane skepticism had to be wrenched out of society. Jean Bodin wrote in response to Weyer's humane skepticism, "Any country which tolerates these skeptics will be struck by plagues, famines, and wars." Now, since it was known that witches caused weather and this unusual weather raged, So did the tortures and executions. How severe did it get? Well, on May 24, 1626, a hailstorm struck central Germany and dropped 1 meter of hail. 2 days later, an Arctic front descended onto Central Europe and bit hard. Rivers froze, grapevines exploded, the rye and barley crops were destroyed. Tree leaves were blackened and fell to the ground and denuded the trees, and people thought it was Y2K. Now, the Lord Mayor of Zeil in Franconia, Johann Langens, wrote, "Everything was destroyed by the frost, which had never happened in people's memory," which was true. Probably a frost that severe hadn't occurred in 500 years. But since it was so unusual, it had to be unnatural given that century's reigning paradigms. Whereupon, continues Johann Langens, whereupon an intensive pleading and begging started among the rabble. Why did the authorities tolerate the sorcerers and witches? The sorcerers and witches must be punished. So punish them the authorities did. In this area of central Germany, in 1626 alone, Bamberg executed 600, Würzburg 900, in Electorate Mainz 900 more were executed, and Westphalia 2,000. That's just a result of the 1626 frost, and those are directly related to weather cooking. Now, science is the only successful means we know of to explain nature, and growth of wealth is the only successful means we have to afford prediction, preparation for, and survival in order to survive extreme weather, which has always happened and always will. But science needs special societal protection, and without that protection, science will just be dialed out, and in its place will be substituted the myths that humans love to create, myths like weather cooking. Thank you.
We need to put a price on carbon in markets, and we need to put a price on denial. We need to put a political price on denial.
Al Gore's back. He just put out his new anti-global warming documentary. It's called An Inconvenient Sequel. Like in his previous film, An Inconvenient Truth, Gore warns about imminent planetary catastrophe if everybody doesn't start using less energy and throwing off less carbon. We've got some inconvenient truths of our own. A new paper points out that Gore's personal home in Nashville, Tennessee, consumes 21 times as much electricity as a typical American home. Can that be true? We weren't sure, so we asked Drew Johnson to come. He's a senior fellow at the National Center for Public Policy Research. He wrote that paper, and he joins us now. Drew, it's hard to believe that someone who cares as deeply about the fate of the Earth as Al Gore does could personally own a home that burns that much electricity. How can that be?
Well, it makes you wonder if he actually believes what he's saying. I mean, this is a guy who has not only this home that burns more electricity in 1 year than the average American burns in their home in 21 years, but he also has 2 other homes on top of it. And here's a guy who's basically exploited concerns about the environment to make $300 million and win the Nobel Prize. So it makes you wonder what his real agenda is.
You know, I remember in the 80s we were all upset when a series of televangelists got into sex scandals. They were in the pulpit telling you not to do X, Y, or Z, and then they got caught doing it. And they were appropriately humiliated, and they were in tears, and they had to leave the public stage for a while. Why do the same rules not apply to this hypocrite?
I wonder the same thing, because just like a Jimmy Swaggart had to distance himself from Christians, environmentalists should be the most furious. We on the right, the libertarians, the conservatives, we can sit and make fun of this guy, but the people who he represents, and basically he is a religious prophet for the religion of environmentalism, and he doesn't walk the walk. I mean, he expects people to, walk to work, ride their bike to work, hang their clothes out on a line rather than using a dryer. And this is a guy who won't take the steps in his own life to reduce his own energy consumption. And some months his energy consumption is 34 times the average American. So we're talking about...
It's hard to believe.
It's unbelievable, yeah.
I have sinned against you, my Lord.
A liberal friend of mine had dinner with him a couple of years ago, and he literally talked about global warming during the meal, and then he got into an SUV and went out to Dulles Airport and flew private back home. And my friend was like a sincere environmentalist, was like, really? How can you do that? But I guess he's a false prophet.
If Greenland broke up and melted, or if half of Greenland and half of West Antarctica broke up and melted, this is what would happen to the sea level in Florida. This is what would happen to San Francisco Bay. A lot of people live in these areas. The Netherlands, one of the low countries. Absolutely devastating.
So here is an offer I should like to make to everyone who has a beachfront lavish property that is now worthless because they believe that sea level rise is going to engulf it. I will guarantee to buy that property for $1, because after all, it's not worth anything to you.
You disagree with them, they threaten you. Thousands of hacked emails showing global warming scientists blasting researchers who do not buy into their doomsday scenarios. One of the scientists threatening to, and I quote now, beat the crap out of my next guest. Pat Michaels from the Cato Institute joins me now. Pat, welcome to the program.
Hey, I'm still here.
Yes, you are. Congratulations. Now, these are emails from within the climate change community, and I want to just quote one of them. Here it is. I'm going to put it up on the screen. This email says, "We can't account for the lack of warming at the moment, and it is a travesty that we can't." That implies that the evidence for global warming is rather weak, or that some evidence is being suppressed therein. What do you say?
What's going on with that quote is Kevin Trenberth from the National Center for Atmospheric Research is saying that our computer models did not anticipate the fact that it hasn't warmed for the last 10 years or so. And in private, to all his colleagues who call themselves the climate community, he says, it's a travesty. If you interview him in public, he's not going to say that. And that's the nature of what's going on in these emails.
There is another email. Isn't there another email where they're talking about a trick, and someone is boasting of using a statistical trick to make the warming look steeper in recent years?
Yes, it was a phrase called hide the decline. And Phil Jones, who wrote that from the University of East Anglia, has said, yes, indeed, he did write that. He said it didn't know what it referred to. He knows darn well what it referred to because he's a co-author on a lot of papers who use this data that he is referring to. It's tree ring data that diverges from the global temperature around 1960. And in order to make it look better, they decided not to extend the tree ring data.
I just want to move on real fast to the threat.
Yeah.
Let me quote that one. "I'm really sorry that you have to go through all this stuff, Phil. Next time I see Pat Michaels at a scientific meeting, I'll be tempted to beat the crap out of him."
The real problem here is the emails showing these guys trying to intimidate the editors of the major scientific journals and succeeding.
Senator Nelson.
Dr. Carey wanted to respond to Senator.
Is it possible for me to respond? You basically.
I did not ask you a question.
Really? Why can't she respond, Senator?
Dr. Curry,
you impugned her integrity. I think she's entitled.
You are welcome to respond, Dr.
I was basically called a denier that I'm denying science. Did you read my written testimony? Are you aware that the IPCC and the consensus has no explanation for the increase of ice in the Antarctic? Are you aware that they have no explanation for the fact that the rate of sea level rise from 1920 to 1950 was as large, if not larger, as it currently is? Are you aware that temperatures have been warming for more than 200 years, and that in the 20th century, 40% of the warming occurred before 1950 when carbon dioxide was not a factor in the warming? Okay, and I could go on and on.
Also, some breaking news just into the newsroom. Turns out the last month was the hottest June on record in the U.S. This is according to this new report just out by the National Oceanic and Atmospheric Administration.
Good evening, folks. It's Diamond with the Oppenheimer Ranch Project Magnetic Reversal News and Shinrin Yoku, bringing you a grand solar minimum update. Tuesday, August 3rd, 11 p.m. Mountain Time, 2021. It's looking quite chilly across the U.S. for most of the beginning of August. Take a look at August 2nd. That was record-breaking, and that's the big story. Record cold sweeps central, eastern U.S. as many European nations suffered a colder than average July. The propagandizing mainstream media simply won't report on the cold, which means a compliant and indoctrinated public aren't privy to the record summer chills currently sweeping Siberia, Europe, and now the U.S. Nor are they aware of the harvest-wrecking freezes that have torn through South America, South Africa of late, and the frogs dying of the cold in Australia. We're not making it up. we're reporting on the facts. Take a look at the temperature anomaly for the first. It pales in comparison to the temperature anomaly for the second that we just showed you. Take a look at that. That is crazy. And to add insult to injury, locations approaching or surpassing official daily temperatures, record lows for the 3rd of August, number in the hundreds. East, all the way in the central U.S., hundreds of records are being broken. And the mainstream, well, they are silent like crickets. And not only that, there is snow reported in Canada in August, right here, August 8th and 9th.
In 1977, the worst winter in a century struck the United States. Arctic cold gripped the Midwest for weeks on end. Great blizzards paralyzed cities of the Northeast. One desperate night in Buffalo, 8 people froze to death in marooned cars. Pat Bushnell was on the road that night.
Traffic just absolutely stopped. I was afraid of being stuck in the car all night long with the cold and the wind, running out of gas. And then what? I think that if we had to go through a real bad winter, just like we just went through, I think we'd have to think about moving someplace else.
Move where? The brutal Buffalo winter might become common all over the United States. Climate experts believe the next ice age is on its way. According to recent evidence, it could come sooner than anyone had expected. At weather stations in the far north, temperatures have been dropping for 30 years. Seacoasts long free of summer ice are now blocked year-round. According to some climatologists, within a lifetime, we might be living in the next ice age.
Hair, grass. Incorrect. 165 volts strong shock.
Let me out of here. I will not be part of the experiment anymore.
He says he's not going to go on. Please continue.
He says he doesn't want to go on.
We must continue.
In nearly every case, the essential results are the same. They hesitate, sigh, tremble, and groan, but they advance to the last switch, 450 volts, because they're politely told to.
The experiment's about obeying orders.
What does that mean?
Everything from the way people talk in elevators to the study of conformity, authority.
And what I said then, and which I still believe, is that global warming really has become a new religion, because you can't discuss it. It's not proper. If you say global, if you look at Linda here today, then all the people who are, notable people, they have said climate change in their talks. All of them have said it. I don't know whether they know what they mean, but they have said it anyway. Everybody talks about climate change. So the American Physical Society, which I was a member, said the evidence is incontrovertible that global warming exists. Now think about that. This is a physical society. And they say you cannot discuss global warming because we believe it's happening. It's like the Catholic Church. There are lots of incontrovertible truth in the Catholic Church, I'm sure. And here there's an incontrovertible truth in a physical society. What is the optimum temperature for the Earth? Is that the temperature we have right now? That would be a miracle. Maybe it's 2 degrees warmer. Maybe it's 2 degrees colder. But nobody has told me what the optimal temperature is for the whole Earth. That in the United States we put 10% alcohol into gasoline. That's the most stupid program America ever done. But all the gasoline should have 10% ethanol in it. And that comes from corn as well, from corn grown in Iowa, I guess. And that's food. So for reason we do this, that food is much more expensive now because we do this. It's very costly and very stupid. But that's what the United States, sometimes the United States do stupid things. And nobody mentioned in nature how important the CO2 is for plant growth. If you have more CO2, the plant grows faster. People use greenhouses and put CO2 in greenhouses to get a higher yield. But now, since the CO2 has increased, we get more plant and more growth faster. It's a wonderful thing, but they don't talk about that in nature. And also, nobody says big trees here in Lindau, for example, the beautiful trees are actually starving. But when a plant developed photosynthesis, there was much more carbon dioxide in the air. And so they could use much more, but there isn't any. So the plants are really starving. But they don't talk about how good it is for agriculture that CO2 is increasing. So this is a difficult slide to see here, but this is the rainfall in lots of places all over the world. But if we focus on this one here, this is the Dust Bowl in the Midwest in the 30s. You see we have the Dust Bowl there. And you look at here in Africa, the huge amount of rain. The climate has changed everywhere, all the time. And that was before we talked about global warming. And the people in the Dust Bowl, people know how to move to California. So the Steinbeck wrote the story of the Grape of Wrath about that. It was a very wonderful story. And so this has happened all the time, happened everywhere, and it's nothing to do with global warming. So when I ask people then, why is the climate change? Why? The temperature has not changed, so why do they talk about it? Another thing which amazes me really is that when they talk about climate change, it's always to the worse. See, the climate also changes to the better. And if climate changes, you have a 50% chance anyway. You got to be better someplace, for heaven's sake. It can't always be to the worse. So then comes the clincher. If climate change doesn't work to scare people, we can scare people talking about extreme weather. That must work. So here is the extreme weather. And the question is the ocean level rising? Well, here is a graph. It's hard to see where you sit again, but this scale is in thousands of years, and this scale is in meters. If you look at the recent scale, then you see here this scale down, you can maybe read that, and this scale here is in centimeters. And for the last 100 years, the ocean has risen 20 centimeters. But for the previous 100 years, it also rose to 20 centimeters. And for the last 300 years, ocean has risen 20 centimeters 100 years. And so there is no unusual rise in the sea level. And to be sure you understand that, I'll repeat it. There is no unusual sight in the sea level. And here is the hurricanes in the United States for 150 years. Hurricanes are supposed to be much worse now because of the weather has gotten 0.8 degrees warmer. I mean, on the average. But you see, there are no such thing. If anything, we've entered a period of low hurricanes. Okay, these are the facts. I don't make up these facts.
I'm just going to briefly summarize the scientific method, because this is what we use when we're analyzing the weather balloons. We don't use models or anything like that, and we don't adjust the data. We just use this particular method. So basically, what a scientist does is he'll do a set of experiments, he'll collect a whole big pile of data and make observations, and we call these facts. And then if he can come up with an equation that will describe all this set of data, then these are called laws. But if you come up with something new, a scientist really wants to explain why is it happening. Laws tell you what happens and how they happen, but they don't tell you why. So the first thing you do then is you make a guess as to why it happens. And we call this a hypothesis. And this is where the scientific method comes in. Because as a scientist, you're then obliged to put your guess to all of the tests that you can think of, and maybe get other people to come up with other tests. And what happens is, if it survives all the tests, then you have a theory. But the unfortunate thing is, if any facts are not explained by your guess or your hypothesis, then it's wrong. So that was summed up famously by Richard Feynman, where he said, it doesn't matter how smart a person is, it doesn't matter how beautiful the hypothesis is, one ugly fact that disagrees with it destroys the whole thing. So the other thing is that if you have two or more theories that explain all the facts, then what we use is the principle of Occam's razor, who was an 11th century monk, and he said, if two or more theories explain all the facts, pick the simplest one. So in thermodynamics, just to explain what thermodynamics is, with the invention of the steam engine, they were trying to come up with ways of improving the efficiency. So you were turning heat from burning fuel into mechanical energy, and that's why the heat is the thermal bit of the name, and the dynamism or the dynamic or movement end is where it got the name thermodynamics. So it's a study of the relationship between mechanical energy and thermal energy. And so there are a number of thermodynamic laws, but one of them, well known, that we'll be using mainly here, is that energy cannot be created or destroyed. However, it can be changed from one form to another, and it also can be transmitted from one place to the other. You could, for example, have a hot glass of water and move it to another spot. You've changed the energy from one side of the room to the other, and so on. What the first law doesn't tell you is the rate at which these processes happen. So how fast can you move heat from one spot to another, or how fast does it change from mechanical to thermal? The first law doesn't tell you that. Instead, we have to resort to measurements. And what we look at is we have a number of different mechanisms have been provided to say how energy can be transmitted from one stage to the other. And these are the only mechanisms that are used in the computer models that try to profile the atmosphere. And what we ask is this enough? Is there something missing? And what we soon discovered was, yes, there is. So up until now, people have been saying conduction, convection, radiation, and acoustic, like I'm talking to you, so I'm sending the energy through the air, but not The air doesn't actually travel to you. We've arranged a simple experiment here that should have been done years ago and will point out an overlooked mechanism for transmitting heat through the atmosphere. So do you want to do that? Or, yeah. So what we've done is we have here a 100 yard, sorry. What we have here is a 100-yard piece of tubing going from one end of the hall to the other, and we have here a plunger. So if you pull that up, Ronan, yeah, if he pulls that up, what you can see is within a few seconds, the liquid is being sucked up in the tube. And if you push it back down again, the liquid is being pushed back down. It's the biggest, longest single-use plastic tube that we have at the moment. So if you just see the red bit there, just lift it up again, you can see how rapid the response is. Now, this is a very controlled experiment. Put it up a bit higher there, Ron. Yeah. This is a very controlled experiment. This experiment, we can calculate how all the different mechanisms contribute to causing us to do this work on the water in the container.
Could I just add, just to make it clear, to just reiterate that I'm applying here work energy. You know, this is PV, I'm moving it. And the work energy is being transmitted through this big, long 100-meter tube, which contains air, and then the energy is ending up over here. The work energy is being done at the other end.
So this is mechanical energy. So this is a mechanism of transmitting energy mechanically. But now, up until now, all the models have been worried about transmitting energy using thermal processes. So we have calculated exactly what the energy transmission is for each of these mechanisms. And you can see here that the overall rate at which the energy is being transmitted down along that tube, it's a very small, narrow tube, but if we were to make a 1 meter square, that would be 2,500 watts of energy is the rate of energy transferred out of that tube, whereas all the methods just used by the computer models and the theories up until now come to less than 2 watts. So for some bizarre reason, people have ignored an energy transmission mechanism that's 3 orders of magnitude greater than any of the others. And we looked to see where people would describe this in the literature, and there wasn't anything. We had to come up with our own name for it, which we called perfection.
But another term would be, you know, true mass energy transmission, mechanical energy transmission.
So this can go against the temperature. That water could be colder or hotter. It wouldn't affect the rate at which the mechanical energy is transmitted. So it's independent of the thermal transmission mechanisms. So in other words, we could freeze the syringe at one end and heat that up to boiling water, and the energy would still, mechanical energy would transmit from the colder to the hotter direction.
Yeah.
So just to give an explanation for how this would happen, here we have the famous Newton's cradle. And if you apply mechanical energy, you can see, imagine that they are the atoms inside in the tube. You can see you apply the mechanical energy at one end, it comes out the other end, but the molecules in between don't move. They vibrate back and forth a bit, but they don't move from one end of the device to the other. And this is what we think is happening.
Yeah, I'll just show it in that, like, again, what we're doing here is, this is obviously not air, but you can see that, like, I'm applying work energy here, and the work energy ends up on the other side, but the balls in between, they're staying where they are. So the energy is being transmitted from one side to the other without this
The interesting thing is that this mechanism that's happening in the Newton's cradle can't be described using the standard models. Maybe now, if they include perfection into it, it might be possible. What we're saying is, we believe that there are greenhouse gases, that they absorb energy and they emit energy. And one of Einstein's famous paper that he published exactly 100 years ago today in 1919, he showed that if a gas was in thermodynamic equilibrium, the rate of absorption by an infrared gas, the rate of absorption was equal to the rate of emission. So in other words, if you increase the amount of infrared active gases in the atmosphere, you will increase the rate of absorption, but at the exact same time, you will increase the rate of emission. So if the gas is in thermodynamic equilibrium, you won't get a greenhouse effect. It won't store the energy. And what we have shown by our data is, yes, the gas, the air is in thermodynamic equilibrium. Now, the climate models have decided to ignore Einstein, when he came up with the equation, he said the rate of absorption is equal to the rate of emission, but there were two types of emission. One was the standard emission from a hot body, a random one. The other one is photo-induced emission. And this is the emission that's used to develop lasers and so on. But what that says is that what will happen is that the infrared active gases will aid the transfer of energy from a hot area to a cold area, but it won't store the energy. So, let me go back to then comparing the night and day. What I'm looking at here is showing you that this is not a one-off event. The one that I showed you in January, here's Tucson for the start of this month, the first week or so. And what I want to draw your attention to is that every day the temperature gets heated up, and every day it cools down at night. But the central bit, the central tropopause, that doesn't go through rapid temperature changes. So what happens to the energy that's stored in the boundary layer? Remember, you're talking of about 2.5 tons of air per square meter. It's a lot of energy. And this is just representing it another way. The bottom axis is time, so this is for the entire month of May. You can see at ground level the temperature zooms up and down, and by the time you get up to 700, that day-night variation is gone. But the lower up ones, they are, but they don't have the same day-night effect. The other thing that I want to point out here is that that energy data, what we're told is that's supposed to be heating up. As you can see here, I've plotted the humidity, the amount of water vapor in grams per cubic meter that was in the atmosphere, that you also get from the same radio balloon data. And if what we are led to believe were true, what we should see is that energy at night, it's vanishing, it's going somewhere. I say it's going out to space, but if it was being trapped by infrared gases, then on the third, slide 3 and slide 4, that's interesting, or slide 6, you have a water vapor there in the atmosphere at the night, so that should be trapping the atmosphere. What it actually does is it cools it. In other words, the atmosphere is behaving exactly as Einstein's law predicts. Not as the global warming things. So in other words, the infrared water vapor is serving to cool the atmosphere at night even faster. And the other thing that you'll see is that that during the day, the water vapor there, that acts to heat up the atmosphere. It's true, because you've got the sunlight coming in, and that sunlight is being absorbed. And if you looked at the spectrum we showed earlier, that's why we see the water vapor things. So we'll go on to our new findings. But what I can say is the data from the weather balloons has shown quite categorically there is no greenhouse effect. Increasing greenhouse gases will increase the rate of absorption, but because the atmosphere is in thermodynamic equilibrium, it also increases the rate of emission. The next net effect is no. There is no greenhouse effect. Increasing greenhouse gases will increase the rate of absorption, but because the atmosphere is in thermodynamic equilibrium, it also increases the rate of emission. The next net effect is no.
So you're saying that actually carbon dioxide is not the driver?
Carbon dioxide is just like any other gas, just like the ideal gas law, Boyle's law, Charles' law, Gay-Lussiac's law. Carbon dioxide isn't any different than any other gas in those laws, and we've discovered that there's a continuum across our solar system of the way atmospheres work, and it's strictly a function. The warmth that we experience is due to two things: the distance from the sun, which means how much solar energy we get, and the amount of atmosphere we have, the atmospheric pressure that we experience here on the surface.
Okay. And now, how was that received? Did you have the IPCC call you up and say, wow, this is fantastic?
We had to change our names to get the first paper published because it was turned down because they knew who we were. And the second time we published it, it was we were required to pull it after they found out that we spelled our names backwards. And it worked the first time. It worked the second time, but it was put on the internet before it was hard copied. Climate denier from What's Up With That turned us in. And so we experienced that not only the climate, well, I call normal people, warmists maybe, and a lot of climate deniers do not like our work. A lot of climate deniers hold out for a little bit of a role with carbon dioxide.
I see. And so, in fact, you're saying that there's no opportunity for scientific inquiry anymore.
It seems that way. And we've actually extended it now. We've actually used the same principles to explain some of the past climate measurements that we've made here on Earth. Same thing. Pressure is the driver. Pressure and the sun.
Okay. Well, we'll be looking forward to reading your work. I'm Michelle Sterling for Friends of Science Society.
Greetings from beautiful Colorado. My name is Ned Nikolov, and I'm a physical scientist with the U.S. Forest Service. Today, I would like to discuss with you the greenhouse effect, the atmospheric greenhouse effect, what it is and how it works. The statements I'm about to make are coming from research that I conducted on my own time, and therefore do not represent the opinions or official positions of the U.S. Forest Service or any other government agency for that matter. So what is the greenhouse effect? Well, it's a term that simply defines the thermal effect of the atmosphere. It's been known for about 200 years now that the presence of atmosphere makes the surface of a planet or a moon warmer compared to the absence of atmosphere, compared to an airless environment when the only source of energy to the surface is the solar radiation. Why it is important to know how the greenhouse effect works? Well, it is because the current radiative greenhouse theory, which claims to explain the greenhouse effect, is actually at the core of all climate projections in existence. So therefore, it is of crucial importance that we make sure the radiative greenhouse theory is physically valid. Because if there are flaws in this theory, or if the fundamental assumptions of the theory are incorrect, that would invalidate all climate projections that we currently have. This is a depiction of how the greenhouse effect is thought to work at present. The figure borrowed from the EPA website is also utilized by Wikipedia. It mirrors a similar drawing published in the 2007 IPCC Fourth Assessment Report. According to the current theory, what makes the greenhouse effect possible is the fact that the atmosphere is nearly transparent to sun's shortwave radiation, but mostly opaque to the outgoing long-wave infrared radiation emitted by the surface. The following mechanism has been assumed to be true for over 100 years. Solar radiation reaching the Earth's upper atmosphere splits into two fluxes, one reflected by clouds on the surface, which is energy lost to the climate system, and another absorbed by the Earth atmosphere system that fuels the climate. About a third of the absorbed solar flux is captured directly by the atmosphere, while 2/3 of it hits the surface. In order to balance the absorbed solar flux, the surface, having a much lower temperature than the sun, emits long-wave radiation. Some of this radiation passes straight through the atmosphere via the so-called atmospheric window located between 8 and 14 micrometer of wavelength. But most of the outgoing long-wave flux is absorbed by greenhouse gases such as water vapor, CO2, and ozone, and re-emitted in all directions, including towards the surface. The effect of this is to warm the Earth's surface and the lower troposphere. Hence, the causative driver of the greenhouse effect is believed to be the atmospheric infrared back radiation, often called greenhouse radiation, and viewed as an extra or external source of heat to the surface. This conceptual model of the atmospheric thermal effect is supported by IPCC. For example, we find the following description in the 2007 Fourth Assessment Report. To balance the absorbed incoming energy, the Earth must, on average, radiate the same amount of energy back to space. Because the Earth is much colder than the Sun, it radiates at much longer wavelength, primarily in the infrared part of the spectrum. Much of this thermal radiation emitted by the land and ocean is absorbed by the atmosphere, including clouds, and re-radiated back to Earth. This is called the greenhouse effect. The notion that absorption and re-emission of outgoing terrestrial radiation by trace gases causes heat to be trapped in the troposphere is postulated in numerous scientific publications, some of which are used as teaching manuals for students, such as this book by Daniel Jacob, a professor of atmospheric chemistry and environmental engineering at Harvard University. Chapter 7 of this book describes the greenhouse effect as follows. To balance this input of solar radiation, the Earth itself emits radiation to space. Some of this terrestrial radiation is trapped by greenhouse gases and radiated back to the Earth, resulting in the warming of the surface known as the greenhouse effect. As we will see, trapping of terrestrial radiation by naturally occurring greenhouse gases is essential for maintaining the Earth's surface temperature above the freezing point. End of quote. The conjecture expressed by Joseph Fourier in 1827 that the atmosphere warms the Earth's surface by acting as an insulator and preventing heat from escaping to space has become a fundamental tenet of the modern climate theory. For example, Dr. Ray Perehumbert, a professor of physics at Oxford University, stated in a 2011 paper that the greenhouse effect works just like fiberglass insulation or low emissivity windows reduce the heat loss from a home. As we'll see later, this explanation is physically totally incorrect. So, to sum up, according to the current unanimously accepted climate theory, the greenhouse effect is a radiative phenomenon caused by heat-trapping gases in the atmosphere that are assumed to reduce the rate of surface infrared cooling to space by absorbing outgoing long-wave radiation and re-emitting part of it back, thus increasing the total energy flux towards the surface. Now that we've overviewed the basic tenets of the radiative greenhouse theory, let's analyze them in the light of known fundamental physical laws and modern satellite observations. We begin with a theoretical question. Can the atmospheric infrared back radiation warm the Earth's surface beyond a temperature set by the solar heating? If most atmospheric long-wave radiation is due to radiant heat emitted by the surface, as depicted on this drawing by the looping arrow in the lower right corner, this implies that the Earth basically raises its temperature by reabsorbing a portion of its own infrared emission. However, such a self-heating mechanism violates the second law of thermodynamics, hence it cannot be real. To fully grasp the issue, it is important to understand the difference between the reflection and re-radiation of infrared energy. Reflection entails no energy absorption and no change in spectral characteristics of the backscattered light. Reflected radiation does not affect the temperature of a reflecting body. Re-radiation, on the other hand, involves absorption of radiant energy by a material body at frequencies of the incoming flux and emission of infrared radiation by the body at frequencies and intensity depending on the body's absolute temperature. Since the temperature of an absorbing body is controlled not just by radiative transfer but other heat exchange processes as well, such as conduction and convection, the process of re-radiation changes both the size and the spectral characteristics of an outgoing infrared flux. Atmospheric gases cannot reflect infrared radiation. they can only re-radiate thermal emissions. That's because they are either transparent to or absorptive of particular infrared spectral bands. Furthermore, according to the Kirchhoff's law, infrared absorptivity of a body equals its infrared emissivity. Thus, substances of high infrared absorptivity, such as water vapor and CO2, do not trap radiant heat, but instead promote radiative cooling. Only materials of very low infrared absorptivity and correspondingly high infrared reflectivity, such as aluminum and silver, can trap radiant heat by reflecting electromagnetic long-wave radiation back to the source. These materials, known in thermal engineering as radiant barriers, possess infrared radiative properties that are opposite to those of the so-called greenhouse gases. Therefore, in order for an atmosphere to trap radiant heat, it must reflect infrared radiation back to the surface, which is not occurring in reality. As a result of all this, the Earth's surface, which is a part of an open system, cannot in principle increase its temperature by absorbing infrared radiation from the atmosphere heated by the surface's own infrared emission. As an extreme example of this principle, consider a campfire radiating infrared flux that heats the skin and clothes of people sitting around it. This increases the infrared emission from the campers' bodies in all directions, including towards the fire. However, this heightened thermal emission does not affect the temperature of the fire. The greenhouse concept essentially claims that the thermal radiation emitted by people sitting around a campfire can increase the temperature of the fire itself, which is thermodynamically absurd. Confusing re-radiation with reflection is a common mistake made even by climate scientists when discussing the greenhouse effect. We now direct our attention towards quantitative estimates of Earth's energy budget that contradict fundamental premises of the radiative greenhouse theory. This figure is from the IPCC Fifth Assessment Report. It shows globally average shortwave and longwave energy fluxes computed from measurements provided by surface and satellite monitoring systems. Solar fluxes are depicted by yellow arrows, while long-wave infrared radiation is represented by orange arrows. Note that the Earth atmosphere system as a whole absorbs 240 watts per square meter of solar radiation, calculated by subtracting the reflected flux of 100 watts per square meter from the above cloud insolation of 340 watts per square meter. Yet the observed long-wave fluxes of the surface are significantly larger, 342 watts per square meter of downwelling infrared back radiation, and 398 watts per square meter of outgoing surface radiation. At the top of the atmosphere, the outgoing long-wave flux nearly balances the absorbed solar flux. Considering that these are real data, a question arises. How does a 240 watts per square meter absorbed solar flux get amplified to more than 340 watts per square meter long-wave fluxes at the surface without violating the energy conservation law, also known as the first law of thermodynamics? The greenhouse theory is typically silent about this question, but when pressed for an explanation, it attributes the enhanced infrared fluxes at the bottom of the atmosphere to a repeated absorption and re-emission of radiant heat by greenhouse gases and the Earth's surface. However, this explanation violates the energy conservation law because, as we pointed out earlier, the process of internal absorption and radiation of infrared energy among system components does not lead to trapping of heat and therefore cannot increase the internal kinetic energy of the system needed to account for the larger near-surface thermal fluxes. Heat trapping is physically impossible in an open system such as a planetary atmosphere where gas volume is not constrained and the dominant mode of heat transport is an uninhibited fluid motion in the form of convection, advection, and pervection, which is infrasound waves. Some scientists try to dodge this issue by emphasizing that the radiative fluxes shown in the IPCC figure balance out. However, the question is not about balance, but how to explain the transformation of 240 watts per square meter absorbed solar radiation into 340 plus watts per square meter long-wave fluxes near the surface without violating physical laws. Here is a layman's example that illustrates the problem. Picture yourself having $240 that you split between two bank accounts. You deposit $79 in one account and $161 in the other. You then start quickly transferring funds between the accounts, whereby you lose $5 in fees for each transaction. Can you reasonably expect to increase your money to $342 in one account and $398 in the other account after X number of transactions? The answer is self-evident, of course not. Hence, the explanation provided by the radiative greenhouse concept for the large downwelling atmospheric infrared flux must be wrong. This flux is not a result of the absorption and re-emission of outgoing terrestrial radiation by greenhouse gases. Another problem with significant implications for the radiative greenhouse theory is the underestimation of Earth's atmospheric thermal effect. For over 50 years, it's been believed that the presence of an atmosphere boosts Earth's global average temperature by 18 to 33 degrees due to a radiative forcing by greenhouse trace gases. Most researchers subscribe to the 33-degree greenhouse effect. However, a study published in 2014 revealed that these estimates were based on a mathematically incorrect formula for calculating the Earth's global surface temperature in the absence of an atmosphere. Conceptually, the issue is that the strength of the greenhouse effect has been evaluated by comparing an observed spherically average global surface temperature to a modeled abstract temperature of a flat disk. This study derived a correct general formula for computing the global average temperatures of airless bodies via spherical integration of the Stefan-Boltzmann radiation law. The new formula was successfully verified against NASA temperature data for the Moon. The study found that the true thermal effect of Earth's atmosphere is about 90 degrees Celsius, or 2.7 times stronger than previously thought. This finding presents additional challenges to the greenhouse theory because a 90-degree thermal effect cannot be explained by known radiation budgets of Earth. The 2014 paper also showed that, first, the Moon is a perfect natural airless equivalent of Earth. Second, the effective radiating temperature of a planet T sub E used by mainstream science to calculate the greenhouse effect is a non-physical quantity that should not be compared to any atmospheric or surface kinetic temperatures. And third, the known atmosphere temperature of a spherical body T sub Na is always lower than the effective radiating temperature, which explains the new estimate of a much stronger atmospheric thermal effect. We now return to the Earth's energy budget diagram to discuss definitions of the greenhouse effect. The peer-reviewed literature formally defines the greenhouse effect as an atmospheric absorption of outgoing long-wave radiation measured as a difference between observed global infrared fluxes at the surface and the top of the atmosphere. The IPCC diagram shows this flux difference in purple. The surface warming caused by the presence of atmosphere currently assumed to be 33 degrees Celsius is considered a consequence of the infrared absorption by greenhouse gases and therefore of secondary importance. This reflects the strong belief in the current climate science that the global surface temperature is controlled by atmospheric infrared long-wave radiation, an idea stemming from the work of Fourier, Tyndall, and Arrhenius in the 19th century. Using this flux-based definition, the Earth's greenhouse effect is estimated according to modern observations at 159 watts per square meter absorbed outgoing long-wave radiation by the atmosphere. The problem is that this infrared flux is utterly insufficient to explain the 90-degree atmospheric thermal effect independently derived by Volokhin and Relez using moon temperature data from NASA. Moreover, this flux-based measure yields physically nonsensical results at the Earth's poles. Thus, the greenhouse effect over central Antarctica has been found to be zero or negative by two independent studies published in 2015 and 2018 using a 13-year-long record of satellite observations. Yet the atmospheric thermal effect over this region, estimated as a difference between mean annual surface temperatures of central Antarctica and the south pole of the moon, is about 144 degrees Celsius. This fact indicates that the flux-based definition of the greenhouse effect has no relationship to the actual atmospheric thermal effect experienced by the surface. Such a conclusion is further supported by comparing latitudinal patterns of the absorbed infrared flux and the surface atmospheric thermal effect. On this slide, figure 1 shows latitudinal variation of the greenhouse effect according to the infrared flux-based definition derived from satellite data by Song et al. 2016. Figure 2a depicts the mean latitudinal surface temperature profiles of modern Earth and the Moon. Moon's surface temperatures came from NASA Diviner measurements and thermophysical models. Figure 2b portrays the meridional variation of the atmospheric thermal effect calculated as a difference between Earth's and Moon's average latitudinal surface temperatures. Comparing figure 2b to figure 1 makes it clear that the atmospheric thermal effect follows an opposite spatial pattern to that of the flux-based greenhouse effect. The atmospheric thermal effect is smallest in the tropics and largest at the poles, while the greenhouse effect is largest at the equator and smallest at the poles. Hence, the infrared flux-based measure of the greenhouse effect does not describe the actual surface thermal enhancement due to the presence of atmosphere. In other words, the atmospheric absorption of outgoing infrared radiation appears to have no relevance to surface temperatures. This slide compares latitudinal variations of the infrared back radiation, also known as greenhouse radiation, and the atmospheric thermal effect estimated using the method described earlier. As with the flux-based definition of the greenhouse effect, we find that the infrared back radiation follows an opposite spatial pattern to that of the atmospheric thermal effect. Compare figures 1 and 2b. This indicates that the atmospheric downwelling long-wave radiation is not a driver of the surface warming attributed to the presence of an atmosphere. Hence, there must be another mechanism controlling the atmospheric thermal effect. We'll see what it is later in this presentation. To summarize, first, the current theory of the atmospheric greenhouse effect has its roots in a 19th century hypothesis proposed as a series of conjectures based on limited amount of data and misinterpretations of experimental lab results. Amazingly, the fundamental premises of this theory have not changed since two famous papers published over 120 years ago. One by Professor Swanny Arrhenius in 1896, entitled On the Influence of Carbonic Acid in the Air upon the Temperature of the Ground, and another by Dr. Niels Ekholm, a meteorologist and friend of Arrhenius, in 1901, entitled On the Variations of the Climate of the Geological and Historical Past and Their Causes. These papers introduced the following tenets that are still at the core of the modern greenhouse theory. A. Trace gases such as carbon dioxide and water vapor trap radiant heat in the atmosphere that is analogous to the heat trapping by glass greenhouses. B. Water vapor exerts a positive feedback that amplifies the warming effect of carbon dioxide. C. Carbon dioxide is the main driver of climate at any time scale, including during the ice ages. And D. An increased opacity of the atmosphere to infrared long-wave radiation due to a higher concentration of CO2 or water vapor would warm the Earth's surface by raising the effective radiating altitude of the planet, thus allowing the temperature lapse rate to be applied over a longer distance. Second, the fundamental premise of the greenhouse theory that the atmospheric thermal effect is due to impedance of surface infrared cooling to space by trace gases has no support in modern satellite observations. In fact, the very definition of the greenhouse effect as an absorption of outgoing infrared flux by the atmosphere not only fails to explain the 90-degree global atmospheric thermal effect at the surface, but also yields physically nonsensical results at the poles, such as a zero or negative greenhouse effect over central Antarctica. Satellite data show that the flux-based definition of the greenhouse effect has no relationship to the latitudinal atmospheric warming at the surface. Third, the infrared back radiation assumed to drive the atmospheric thermal effect also shows no meaningful relationship with the degree of atmospheric thermal enhancement across latitudes. Fourth, the assumption that repeated absorption and re-emission of thermal radiation by greenhouse gases somehow increases the overall internal kinetic energy of the lower troposphere is not supported by either thermodynamic theory or observations. The attempt to explain observed near-surface thermal fluxes which exceed 340 watts per square meter with the measured absorbed total solar flux of 240 watts per square meter using only radiative transfer theory leads to violation of the energy conservation law, also known as the first law of thermodynamics. Hence, such an explanation must be physically incorrect. Fifth, the proposed self-heating mechanism through recycling of infrared long-wave radiation between surface and the atmosphere adopted by the greenhouse theory violates the second law of thermodynamics, also known as the law of increasing entropy. That's because a physical body cannot increase its temperature by absorbing infrared long-wave radiation from another object that has previously been heated by the body's own thermal emission. Sixth, there is no physical evidence that the atmosphere acts as a thermal insulator to the Earth's surface as assumed for nearly 200 years. Because thermal insulation requires materials that have either very low thermal conductivity and thus retard convective heat exchange, or a very low infrared absorptivity and high infrared reflectivity that deflects thermal radiation. These properties are opposite to those of greenhouse gases, which is why such gases have never been employed as thermal insulators in engineering applications. We might now ask the question, what is the solution to the insurmountable physical problems facing the greenhouse theory? Fortunately, a solution exists in the form of an alternative, full-fledged concept based on modern observations that explains the atmospheric thermal effect and climate change in a whole new way. First, we address the question, what is the physical nature of the atmospheric thermal effect, or ATE for short? To find out, we adopted a top-down analytical approach that has not previously been attempted in climate science. Our method rests on three key premises. A, the mechanisms governing Earth's climate are not unique to our planet, but operate on other solar system bodies with rocky surfaces as well. This premise stems from a fundamental postulate in physics that natural laws are invariant with respect to space-time. B, if the above is true, then the Earth's long-term global surface temperature must be a part of a cosmic continuum of planetary temperatures spanning the solar system and controlled by a common set of drivers. And C, finding the correct functional form of this continuum should reveal the true cause of the atmospheric thermal effect on Earth and other planets. We gathered planetary data from numerous published sources. This slide shows the planets and moons in the solar system for which sufficient data currently exists to be included in our analysis. We selected 3 planets and 3 moons covered by quality data representing a broad range of radiative regimes, atmospheric conditions, and thermal environments. For example, the solar radiation at the top of the atmosphere ranges from 1.5 watts per square meter at Triton to about 2,600 watts per square meter at Venus. The long-term global surface temperature varies from 39 Kelvin on Triton to nearly 700 Kelvin on Venus. Planetary atmospheres cover a large continuum from the Moon's airless environment to the massive atmosphere of Venus, exerting a surface pressure of 9,300,000 pascals. The spectrum of atmospheric compositions is equally impressive. In searching for drivers that can explain the variation of global surface temperatures across these diverse bodies, we decided to let the data tell a story rather than employing a preconceived theory in the analysis that could bias our conclusions. Hence, we applied a classical technique called dimensional analysis, or DA for short, designed to infer physically meaningful relationships from actual measurements without having a theoretical knowledge about a phenomenon. DA has been successfully employed in fluid mechanics, physics, and other fields of science, as well as in various areas of engineering for about 200 years. It's a proven method for deriving physical relationships that are independent of measurement units, in accordance with the fact that laws of nature operate using dimensionless quantities. Our dimensional analysis reduced the large number of planetary input parameters to a few dimensionless variables, while suggesting 12 possible models, shown on this slide, that had to be investigated for viability through a nonlinear regression analysis. On these plots, the horizontal axis showed dimensionless products composed of greenhouse gas densities and partial pressures, solar irradiance, and total surface atmospheric pressure and near-surface air density. Vertical axes represent the atmospheric thermal enhancement, or ATE, defined as a ratio of a body's observed global surface temperature under the current atmosphere to the body's hypothetical global surface temperature in the absence of either greenhouse gases or an atmosphere. Dimensional analysis yielded this temperature ratio as a measure of the atmospheric thermal effect. Out of all models, only model 12 produced a very tight and highly accurate relationship describing ATE as a function of total surface atmospheric pressure, P. The second best model in terms of a curve fit was model 1, which employed partial densities and partial pressures of greenhouse gases as predictors. A comparison of models 1 and 12 in this figure using linear vertical axis shows that model 12 was vastly superior to model 1. The rest of the regression models did not produce any meaningful relationships. Note that the plot of model 12 uses logarithmic axis. Upon taking anti-logarithm, we arrive at this curve describing the response of the atmospheric thermal effect to surface atmospheric pressure across the solar system on a linear scale. This represents the core of our discovery regarding the physical nature of the atmospheric effect. The vertical axis is the relative atmospheric thermal enhancement, abbreviated as rate, defined as a ratio of two long-term global surface temperatures, one measured under the current atmosphere, T sub SB, and another estimated in the absence of an atmosphere, T sub NA. The no-atmosphere temperature T sub NA is calculated using the new airless integral spherical formula by Volokhin and Relais 2014, which has been verified against NASA data for the Moon, Europa, and Callisto. Therefore, this temperature ratio quantifies the degree, in relative terms, to which the presence of an atmosphere warms the surface. Note that the absolute atmospheric thermal effect is the arithmetic difference between T sub SB and T sub NA. The horizontal axis is the observed mean surface atmospheric pressure on a planetary body, the only variable in our analysis that accurately predicted the relative atmospheric thermal effect over a vast range of physical conditions. While the relative atmospheric thermal enhancement only depends on surface air pressure, the absolute atmospheric thermal effect depends on both pressure and total solar irradiance or distance to the sun. As discussed in our 2017 paper, to be presented in a minute, this curve possesses the mathematical features of a new planetary-level microphysical law, including accuracy, robustness, and a broad scope of validity. It places the Earth's baseline temperature in the context of a cosmic continuum of climate drivers, which is something that the relative greenhouse theory has not been able to achieve. For those who are mathematically inclined, this slide shows the formula for calculating the baseline average global surface temperature of planets and moons as a product of two terms: the no-atmosphere temperature T sub NA, which is basically a function of solar irradiance or the planet's distance to the sun, and a dimensionless double exponential term quantifying the relative thermal enhancement of the atmosphere, which is a function of the mean surface air pressure. The second term describes the red curve we discussed on the previous slide. The expression for the average airless global temperature T sub NA was derived by analytical integration of the Stephens-Boltzmann radiation law over a sphere as described by Volokhin and Relais 2014. This semi-empirical equation reveals that the long-term baseline temperature of a planetary body, T sub SB, is only a function of two drivers: the top of the atmosphere solar irradiance and total surface atmospheric pressure, and that atmospheric composition plays no role in determining the planet's temperature. Hence, the so-called greenhouse gases are thermodynamically not different from any other gases such as nitrogen and oxygen, and their contribution to a planet's baseline surface temperature is only through their partial pressures and not through their infrared radiative properties. The macro-level pressure-temperature relationship across planetary bodies discovered by our research has fundamental implications for the current climate theory and our understanding of climate drivers. These are as follows. First, the atmospheric thermal effect is a form of compression heating caused by air pressure that is independent of atmospheric composition. Pressure as a force applied over a unit area enhances the energy received from the sun, since energy is a function of force, and the kinetic energy of a gas measured in joules is defined by the product of pressure times volume according to the gas law. In other words, the atmosphere warms the surface adiabatically, not radiatively as believed for nearly 200 years. Second, the atmospheric infrared backradiation is a byproduct of the atmospheric thermal effect, and as such it does not drive Earth's climate. The latter is controlled by the sun and total air pressure, which is a function of atmospheric mass and gravity. This means that the radiative greenhouse effect does not exist in reality. The confusion originated from the fact that the downwelling infrared radiation is easily measurable and has been measured since the 19th century, while the adiabatic pressure-induced heating is hidden as an underlying cause and requires a cross-planetary analysis like ours to detect. The adiabatic compression heating of the surface and the lower troposphere explains why the flux of atmospheric infrared back radiation on Earth is 42% larger than the total absorbed solar flux by the planet. On Venus, the discrepancy between these fluxes is extreme due to a 93 bar atmospheric pressure. The infrared back radiation at the Venusian surface exceeds 12,500 watts per square meter, while the absorbed solar flux is only 65 watts per square meter. The atmosphere does not trap radiant heat. It adiabatically enhances the absorbed solar energy through the force of air pressure, which is a mechanism deeply misunderstood in climate science. Third, contrary to the claim made by the greenhouse theory, the Earth's climate has no tipping points, since the baseline global temperature of a planet is a smooth function of solar luminosity, distance to the sun, and total atmospheric pressure. Fourth, non-condensing trace gases such as carbon dioxide, methane, and nitrous oxide have no measurable impact on the global surface temperature due to their minuscule partial pressures in the atmosphere. Fifth, human carbon emissions cannot in principle affect global climate because they do not alter atmospheric pressure in any significant way. Sixth, the bulk of planetary albedo is a byproduct or consequence of the climate system and does not control the global surface temperature. However, a small fraction of the albedo is modulated by solar activity and impacts planetary temperature on decadal to centennial timescales. We'll address this topic again later. It should be pointed out that the current climate theory does not consider direct thermodynamic effects of atmospheric pressure on global temperature. In the greenhouse concept, pressure only impacts surface temperature through the broadening of infrared absorption bands of greenhouse gases. Thus, the role of pressure as a force controlling the temperature of a gas dictated by the gas law has mostly been ignored in climate science. Our discovery draws the researchers' attention back to this fundamental thermodynamic driver. The pressure-temperature relationship discovered in our analysis of planetary data is qualitatively quite similar in terms of shape to the pressure-temperature functions known in other physical systems as illustrated by this slide. This gives credence to the notion that our empirical model describes a macro-level physical reality. Our discovery about the physical nature of the atmospheric thermal effect, currently known under the incorrect name greenhouse effect, is described in this 2017 paper, which I strongly recommend to everyone interested in the technical details of this new climate science paradigm. The paper is available as an open access online. You may notice that the regression coefficients of our empirical pressure-temperature model presented in this video differ slightly from those listed in the paper. That's a result of using more recent and better baseline temperature data for some planetary bodies such as Venus, Titan, and Earth. Although the direct effect of pressure on gas temperature is fundamental to classical thermodynamics and a part of standard atmospheric physics, pressure is not an explicit component of the current climate theory exclusively focused on the purity of radiative greenhouse effect. As a result, climate scientists do not consider air pressure to be a driver of surface temperature except via its effect on the broadening of gas absorption lines in the infrared spectrum, which is not a thermodynamic phenomenon. Hence, it might be informative to discuss some examples illustrating the critical role of pressure in determining atmospheric temperatures. The most common effect of pressure on air temperature is the observed cooling with increasing altitude in the troposphere. The decrease of air pressure with height is the reason for the drop of ambient temperature at a rate of about 6 degrees Celsius per kilometer as one ascends in elevation. This explains why tall mountain peaks, located even at the equator, such as Mount Kilimanjaro, are cold enough to support permanent glaciers, while their foothills host lush subtropical flora and fauna. The temperature drop with elevation is called adiabatic lapse rate. The word adiabatic means changing the internal kinetic energy and temperature of a gas parcel without gain or loss of heat, that is, without a heat exchange with the surrounding environment. Adiabatic heating and cooling are only possible through changes in the internal gas pressure. Thus, the negative adiabatic lapse rate observed in the troposphere is the result of a temperature change with pressure and the decrease of pressure with height. In mathematical terms, dt dz equals dt dp times dp dz. The vertical convection in Earth's atmosphere is nearly an adiabatic process, since air parcels heated by the surface cool mostly by rising up and expanding into lower pressure levels aloft. While the decrease of pressure with altitude is the reason for the existence of a lapse rate in the troposphere, the magnitude of this lapse rate depends strongly on the intensity of solar heating, atmospheric moisture, and wind speed. Standard dry air has a lapse rate of minus 9.8 Celsius per kilometer, while saturated moist air cools at a rate of about 5 degrees Celsius per kilometer. The environmental lapse rate usually falls between these two extremes. Intense solar heating during summertime can cause a super adiabatic lapse rate that is greater than minus 10 degrees per kilometer. Some climate scientists claim that the lapse rate is caused by radiative properties of greenhouse gases, which is thermodynamically completely false. Perhaps the most striking example of pressure heating in the atmosphere are high-pressure systems called omega blocks or heat domes that are formed by a wavy and meandering jet stream. One such event recently occurred over the Pacific Northwest. A high-pressure system got lodged for several days over Washington State and British Columbia, Canada, at the end of June of 2021, causing a record-smashing heat wave with surface temperatures soaring over 43 degrees Celsius or 110 degrees Fahrenheit in most places. The town of Lytton in western Canada, nestled between mountain ranges, experienced lethal temperatures of 49.4 degrees Celsius or 121 degrees Fahrenheit on June 30th. In a few hours, the excessive heat stripped trees of their green leaves and ignited fires that consumed 90% of the small town. This incredible heat was caused by sinking air that the high-pressure system pushed down from higher altitudes and adiabatically compressed near the surface. Another contributing factor were the easterly katabatic winds generated by the high-pressure system due to a clockwise rotation of the air that came down the mountain slope and also got heated by compression. Some commentators rush to link this rare heat wave to anthropogenic climate change, but the reality is that atmospheric CO2 played no role in this event. Research conducted after 2017 led to the expansion of the Nikolov-Zeller or NZ model. Using latitudinal thermal observations from several planets and moons provided by NASA, we developed equations for estimating the long-term baseline temperatures at 5 key latitudes in addition to the global mean. Latitudinal temperatures were coupled to the average global temperature via thermal gradients that were found to be accurately predictable by the average near-surface atmospheric density, which in turn, according to the gas law, is a function of total surface atmospheric pressure and the global average temperature. The NZ model was also extended to include the effect of cloud albedo variations on the global surface temperature. These augmentations and their implications for a new understanding of the drivers of Earth's paleoclimate and modern climate change were presented in two separate videos at the 101st meeting of the American Meteorological Society in January of 2021. The videos can be viewed on YouTube at a channel called Truth and Insights. This slide shows screenshots from the two videos. To find them quickly online, please Google the titles listed under the screenshots. These videos complement the information presented here by providing a more comprehensive picture of an emerging climate science paradigm that has the potential to solve the current climate crisis through a new enlightenment. We conclude this presentation by highlighting some principal differences between the greenhouse hypothesis originated in the 19th century and the new Nikolov-Zeller climate concept based on a planetary temperature model derived from modern observations obtained throughout the solar system via a robust mathematical analysis. The greenhouse theory assumes that the Earth's atmosphere raises the global surface temperature by 33 degrees Kelvin, while Nikolov and Zeller found the atmospheric thermal effect to be around 90 degrees Kelvin, or 2.7 times stronger than assumed for nearly 100 years. The NZ model fully explains this thermal enhancement in the context of a cosmic continuum defined by 6 planetary bodies spanning the breadth of the solar system. The greenhouse theory claims that the atmosphere reduces the surface infrared cooling to space through trapping of radiant heat by greenhouse gases. Nikolov and Zeller discovered that the atmosphere heats the surface adiabatically through a gravitational compression of air. The resulting air pressure enhances the energy received from the sun by adding force to the gas system, a mechanism that is misunderstood and ignored in the current climate science. Since the atmosphere is a convective fluid operating in an open system, it cannot and does not trap heat. The greenhouse hypothesis argues that the global surface temperature is sensitive to changes in greenhouse gas concentrations. Hence, human carbon emissions can impact climate. Nikolov and Zeller found that the global baseline temperature of planetary bodies is independent of atmospheric composition. Therefore, non-condensing trace gases have no measurable influence on climate due to their small partial pressures. The greenhouse concept regards atmospheric carbon dioxide as a key driver of climate on all timescales. The NZ concept identified different drivers at different timescales. Over decades to centuries, the global climate is controlled by small fluctuations of cloud albedo around a baseline induced directly or indirectly by sun's magnetic activity. On timescales of thousands to millions of years, variations in total atmospheric mass and surface air pressure change the planet's global baseline temperature and meridional temperature gradients, creating the polar amplification phenomenon observed in the geological records.
We have to not be afraid. Fear may produce a television audience, it may generate cash for an advocacy group, but fear paralyzes us, it freezes us. And we really need to put that behind us as we move into a new era of managing complexity. Because, look, here's the independent, the future of the earth. Is this the end of the world? Earthquakes, hurricanes, floods. What is happening to our planet? Is this the end of the world? No. We live on an active planet. Earthquakes are continuous, 1.5 million a year, or 3 every minute. A Richter 5 every 6 hours. A major quake every 3 weeks. This is all the earthquakes in California in the last week. There's a quake the size of Pakistan every 8 months. This is Kobe in Japan. Despite building codes, the buildings just topple. Very good building codes. At any moment on our planet, there are 11 lightning strikes every second. There are 1,500 electrical storms on the planet at any moment. A tornado touches down every 6 hours. A tidal wave crosses the Pacific every 3 months. There are 90 hurricanes a year, 1 every 4 days. It's constant. Is this the end of the world? No, this is the world. And I think it's time we knew it.
It will be informative to examine a popular tabletop demonstration purported to show the heat-trapping properties of carbon dioxide in Earth's atmosphere. This is the so-called greenhouse effect in a bottle experiment, frequently used to teach students about how the anthropogenic global warming is supposed to work. Here is an example. First, let's answer the question, what made the bottle filled with carbon dioxide warming up more than the control bottle containing normal air? Well, the CO2 bottle absorbed more infrared radiation from the sun lamps than the air-filled bottle. This part of their explanation was correct. Since gas volume is constrained by the rigid walls of the bottles, gas expansion and convective heat exchange with the surrounding environment were hampered in both cases. But because CO2 absorbs more thermal energy than air, it also expands stronger than air. As a result, the gas pressure in the CO2 bottle rises to a higher level than the pressure in the air-filled bottle. This boosts the temperature in the CO2 bottle above that of the air-filled bottle. However, this does not demonstrate a heat-trapping property of carbon dioxide. Here is why. Gas systems operating under a fixed volume, as in this experiment, are called isochoric in thermodynamics. Their behavior is described by the Gay-Lussac law, which states that in a constant volume system, pressure is proportional to temperature. One can also state that in isochoric system, temperature is a linear function of pressure. However, the atmosphere is not an isochoric system because its volumetric expansion is not constrained by a rigid barrier. The atmosphere operates as a constant pressure system, also known as isobaric system, because the surface pressure is determined by gravity and the atmospheric mass above a unit surface area. Isobaric systems are governed by Charles' law, which states that under a constant pressure, gas volume is proportional to temperature. One can observe Charles' law at work in Earth's atmosphere by examining the latitudinal variation of the height of the tropopause. Tropopause is the altitude where vertical convection induced by surface heating runs out of energy and ceases to push the cloud deck any higher, while at the same time making the air temperature stop decreasing with elevation. That is, the elapse rate becomes zero in the tropopause. The tropopause height is an indicator of atmospheric volume. In the tropics and subtropics, the tropopause is located at 16 to 18 kilometer altitude, while in the polar regions it is found at 8 to 10 kilometer altitude. This suggests that the atmospheric volume is nearly twice as big in the tropics as it is at the poles. That's because the solar heating is much stronger at lower latitudes than it is in the polar region. Air parcels heated at the surface rise and cool adiabatically in the free atmosphere by expanding into lower pressure levels aloft. However, a gas trapped in a bottle cannot cool through expansion. Impeding convective heat exchange and adiabatic expansion makes the results from this bottle experiment inapplicable to the real atmosphere, since bottle gases represent a completely different kind of a thermodynamic system governed by a different law compared to the gas system of an open atmosphere. If a CO2 parcel would be allowed to freely expand when heated by infrared radiation, its final temperature will be no different from, or perhaps even cooler than, that of an unconstrained parcel of normal air absorbing even lesser amount of infrared radiation. Therefore, this bottle experiment demonstrates nothing more than the well-known Gay-Lussac law of thermodynamics and does not provide an illustration of radiant heat trapping by CO2 as claimed by the current theory. Another problem with the experiment shown in this video is that the greenhouse bottle contained over 80% carbon dioxide, since it was capped immediately after pouring the vinegar that started the chemical reaction releasing CO2. The Earth's atmosphere currently only has about 0.04% carbon dioxide that is expected to rise perhaps to about 0.06% by the year 2100. Over the past 500 million years, atmospheric CO2 has not exceeded 0.25% or 0.25%. The CO2 concentration in the experimental bottle is over 300 times higher than that. This makes a big difference in how much warmer the greenhouse bottle could get. If the control bottle contained a pre-industrial CO2 concentration of 0.028% and the greenhouse bottle was at the present CO2 level of 0.0415%, then even this constant volume experiment would likely have shown no measurable difference in temperatures between the two vessels.
We eat food made of carbon. We live in homes made of carbon. Our children are made of carbon. How can carbon be our enemy?